Now moving on to the experimental procedures regarding the equipotential lines and the electric field mapping. Now today we are going actually to be studying two different configurations. Over here we have the parallel plate configuration, and over here we have the dipole configuration. So first off, you are going to be placing that conducting paper or the parallel plate configuration, you are going to place it on that wooden board. And then you have to make sure that the spring contacts, they are actually lying right above these two silver electrodes over here. And then you have to tighten them very well until you make sure that there is maximum contact between the spring contacts and the silver electrodes. Now on the other side over here we have a DC power supply, and therefore the role of the DC power supply would be to supply our conducting paper with enough voltage in order actually to locate several points that have the same electric potential. So what we are going to do next is we are going to be connecting that conducting paper in parallel with that DC power supply over there. So we are going to bring one connection from the positive terminal, and we are going to connect it to one end of these spring contacts, and then we are going to bring another connection from the ground, and then we are going to connect it to the other end of that conducting paper. So now we have the conducting paper and the DC power supply connected in parallel. Now what we need to do next is we need actually to use some detector in order to locate in that region points that have the same electric potential. How can we do so? First off, we need over here to bring a voltmeter. So on one side over here we have a voltmeter. Then we are going to be bringing one connection from the ground and connect it across the COM on that voltmeter. Then you have to bring over here a probe. A probe, like I told you before, it is actually a voltage locator. So it is used in order to locate points that have the same electric voltage. So over here you are going to be connecting that probe to the voltage port over there on that voltmeter. So now what we need to do next is actually we need to be applying a certain potential, a certain voltage between these two silver electrodes over here. So in that case, let's say we are going to be applying a certain arbitrary voltage of 6 volts. So what you are going to do is you are going to be placing the tip of that probe on that silver electrode over here, which is connected to the positive terminal. And then by looking at that voltmeter over there, and by varying with the voltage of the DC power supply, you are going to be incrementing the voltage up to 6 volts. So it's approximately around 6, 5.9 or 6 or 6.1. Now, what do we expect to have on that other silver electrode? Since the other silver electrode is actually connected to the ground, therefore we expect to have a value which is close to 0 voltage. So by placing the probe over there, we can see on that voltmeter that we have a value of 200 millivolts or 0.2 volts, which is basically a very insignificant value. So we can actually neglect it and approximate it to 0. So now we have between these two silver electrodes over here, we have a region of uniform distribution of electrical charges. So that region over here between these two silver electrodes, it consists of a region of uniform electric charges. Therefore, we expect that the electric field in that region to be a uniform electric field, since we have a uniform distribution of charges. Now if we look at that report over there, we can see that we have 3 different voltages, meaning that you have to pick 3 different voltages between these two parallel plates. So these voltages are going to be picked in an arbitrary manner. So for example, let's say we are going to start at that point over here. That point that corresponds to a certain voltage of 5.57. But moreover, if we look at that conducting plate, that conducting paper, it is actually equipped with coordinates, x coordinate and y coordinate. So therefore you would be able actually to locate the x and y coordinates of each point. So for example, for that first point of 5.58, you are going to write down over here that V1 is equal to 5.58. Then in that first row over here, you are going to be writing the coordinates that correspond to that first point, which are x equal to 9 and y equal to 2. Now since we have over here parallel plates configuration, therefore we expect that the other equipotential points to be located along the same straight line, meaning that the other points that have the same electric potential are going to be located along that same straight line. So the geometry of the equipotential lines in that case is actually dictated by the geometry of the configuration that you have. So since we have parallel plate configuration, and therefore they have a uniform distribution of charges between them, therefore we expect that all equipotential lines to be parallel to each other and parallel to these plates over here. So by moving forward to our next point, which is around 5.56, which is close to the previous one, you are going to record its coordinates now in the second row over here. So x equal to 9 and y is equal to 3. Now you have to keep one thing in mind, that not all equipotential points in that experimental part are going to be exactly the same. Like they might differ by 0.2 or 0.4 or 0.5. And that is because that conducting plate is not well fastened against that wooden board. Therefore, some electric charges, they might be fleeting that board. They might be fleeting that plate. So you have to keep that in mind. Now you keep moving forward until you find the third equipotential point, which is located at around x equal to 9 and y equal to 4, and then you record it in that third row over here, and then you carry on until you cover the entire length of that conducting plate. And that would be for the first voltage, which is V1 equal to around 5.6. Now you have to choose second arbitrary voltage. Now let's say that we move the probe to the middle. So we move the probe to the middle of that configuration table over here, of that configuration plate. Now in the middle we expect to have half of the voltage that we initially applied between these two plates. So initially we have applied the value of 6.2. So over here, if we look at that DC current power supply, at the DC power supply, we can see that we have applied a certain voltage of around 6.2. So we expect over here in the middle to have half of that value, which is approximately half. Over here we are reading 3.3 on that voltmeter. Now for that part, you are going to write down over here that V2 is equal to 3.3, and then you are going to record in that first row the coordinates for that first value, which are x equal to 6 and y equal to 2. And then you work your way up to the second point until you locate the second point, which is around now x equal to 6 and y equal to around 2.75, and then you keep working your way up until you locate the third point, which is around x equal to 6 and y equal to 4, and then you keep working your way up until you cover the entire length of these two plates. And as we can see over here, actually, that each equipotential line is actually parallel to the previous one. So the entire equipotential lines that we are going to locate between these two plates, they are going to be parallel to each other and parallel to these two plates. And then you repeat the same thing for the third arbitrary voltage. So now let's say you move the probe to the other part, to the other end of that parallel plate configuration. You locate a certain arbitrary voltage, which is now of 1.2. So as we can see, as we are moving away from the electrode, which is connected to the positive terminal of the DC current, the voltage is actually decreasing. So now you record the coordinate for that point, which is x equal to 3 and y equal to 1, and then you work your way up to cover the entire length of that plate. Now you have to keep one thing in mind. We said over here that we have a uniform charge distribution between these two plates. However, as you approach the plate, as you approach the edge of that plate, the values or the equipotential values, they are not going to be located along the same straight line, but rather the equipotential line is going to start to curve toward the edge. Because at the edge, that uniformity of charges is actually lost. So at the edge of each plate, we don't have the same uniformity of charges as the one that we have in the middle. Therefore, at the edge, each charge is going to be behaving as a single charge. And we have seen before that for a single charge, we have circular equipotential lines. So that's why over here at the edge, we are going to have the so-called the edge effect. So the edge effect is actually due to the fact that at the edge of each plate, the uniformity of the charge distribution is actually lost. Therefore, each electric charge will behave as a single charge. Therefore, you are going to have the equipotential line being curved toward the outside at each edge. So we have to keep that in mind. And that would be it for the first part. Now for the second part, we are going to be repeating the same thing all over again, but instead of using parallel plate configuration, now we are using a dipole configuration. And as we have done before, you have to make sure that the spring contacts, they are at maximum contact with each silver electrode. And like we have done before, you have to make sure of the voltage that you are applying at each end of that dipole. So over here, the dipole which is connected to the positive terminal of the power source is at around 6.1, it's close to 6.1, while the other dipole is at around 160 millivolts, which is close to 0. Now, since we have a different configuration, therefore we are going to be obtaining a totally different geometrical shape for the equipotential lines. So before we saw that the equipotential lines were parallel, since we had parallel plate configuration. Now over here, since we have a dipole configuration, therefore we should expect to have circular equipotential lines or semicircle equipotential lines. So in that case, we are going to be in a similar manner to what we have done before. Moving on to that table, you are going to be picking 3 different arbitrary voltages. So let's pick V1. Let's say that V1 is over here at that point. Okay, so V1, as we can see on the voltmeter, is at around 4.73. So you are going to record over here V1 equal to 4.73, and then you are going to record its corresponding coordinates, x equal to 12 and y equal to 1. But now how are you going to work your way up? Now, we cannot work our way up as we have done in the previous case. But over here, since we have a dipole, therefore we should expect that the equipotential lines to be lying along a circular shape, or to be forming a circular shape. Therefore, we are going to be working our way up in that way, in a diagonal way. And as we can see now, the second point, which has the same equipotential as the previous one, is at around x equal to 11 and y equal to 2. And then you keep working your way up in that manner until you are forming actually a semicircle shape around that first dipole over here. So for the first dipole, as we can see, the first equipotential line is going to have a semicircle shape. Now let's consider that we have moved to the middle part between the first charge and the second charge. So we are actually considering the distance which is halfway through that dipole. Now in that case, since we are working halfway between that dipole, therefore we should expect to have the same charge distribution from that first charge and from that second charge. So over here in the middle, we have the same charge distribution from that dipole. So we should expect that semicircle shape to be flattened out in order to become over here a straight line in the middle. So over here, for example, if we start at that point, at V2 equal to 3.10, you record over here V2 equal to 3.10, and you record its corresponding coordinates, which are x equal to 6 and y equal to 1. Then you work your way up. So now we have the second point, which is at around x equal to 6 and y equal to 2. Then we have the third point at around okay, over here we have slight changes in the voltages, because like I have told you before, if the paper is not well fastened, errors might occur. Okay. Alright, so now as we move to the third point, we can clearly see that it also has the same value for the electric potential, and it is located now at x equal to 6 and y equal to 3, so on and so forth until we carry on until we reach the end of that conducting plate. So as we can see in the middle, since we have the same contribution from both sides, therefore we are going to have a straight line for the equipotential line. So over here we started with a semicircle shape. Now as we start moving away from that dipole, the shape starts to flatten out until it becomes a straight line over here. Now as we start approaching the second part of that dipole, Now that straight line, equipotential line over here is going now to start to curve again. So it's going to start to regain back its semicircle shape until we reach over here a perfect semicircle around that other dipole. So for V3, you are going to pick also an arbitrary point. Let's say over here V1 equal to 1.4 or 1.5, and then you keep working your way up in a semicircle manner until you locate all the other points that have the same electric potential, and of course you have to keep recording their coordinates. And that would be for the second part. Alright, now let me clarify some of the experimental questions or some of the questions that are actually asking you in that report. Over here they are asking you to plot the three equipotential lines on a graph, and based on your graph you have to sketch the electric field lines of the parallel plates. So let's say over here we have the following: two conducting plates, two conducting parallel plates, and like I said, between them you have a uniform charge distribution, so we expected for the equipotential points to be located actually along the same straight line, and the same thing in the middle, and the same thing over here near the edge, near the other edge. However, I told you that near the edge of each plate you have something called the edge effect. So over here these equipotential points are not going to be located along the same straight line, but rather they are going to start to curve toward the outside. So we are going to have that shape. And the same thing on the other edge. We are going also to have the so-called edge effect. That would be for the equipotential lines. Now they are asking you also to draw or to sketch the electric field lines. So the key word over here is actually to sketch. So there is no need actually to rely on any values in order to sketch the electric field. We know from previously that the electric field is actually perpendicular to the equipotential lines. So in that case, the electric field is going to be directed from the positive plate toward the negative plate, but moreover, it's going also to be perpendicular to these equipotential lines. So as we can see over here, the electric field directed from positive to negative, and it is also perpendicular to these equipotential lines. That would be for the parallel plate configuration. Moreover, they are asking you over here in question number 1 to describe and explain what you observe in each graph. So in the graph, what you need to be explaining is the shape of the equipotential lines and the fact that you have a uniform charge distribution, and then you have to explain that edge effect at the end, and then you have to explain how the electric field is directed from positive to negative while being perpendicular to the equipotential lines. That would be actually the description. So it's going to be a written description. That would be for the first configuration. Now for the second configuration, for the dipole. So let's consider that we have the following dipole, positive and negative. Like I said, near that first charge, you are going to obtain a semicircle shape for the equipotential points. So all the equipotential points are going to be lying along that semicircular shape. Now as you start moving away from that charge, that shape is going to start to flatten out bit by bit until you reach the middle over here, where you are going to obtain a straight line, since we have the same contribution from both charges. And then after you move away from that halfway position between these two charges, now the equipotential line is going to start to curve again, so on and so forth, until you reach the other charge where you have a perfect semicircular shape all around it. So over here what I'm actually drawing is I'm drawing the equipotential lines which have a semicircular shape for the dipole configuration, while in the middle over here you are going to have a straight line. Now after drawing the equipotential lines, now we need to draw actually the electric field lines. And again, the electric field lines over here are going to be perpendicular to the equipotential lines. So first off, we start by drawing the middle electric field force, or the middle electric field line, which is going to be directed from positive to negative while being perpendicular to each equipotential line. However, as you move away from that middle portion, now the electric field lines are going to start to curve in order to adjust for that curvature in the equipotential lines. And the same thing over here. They are going to start to curve and be directed from positive to negative in order to account for the curve in these equipotential lines. So always do not forget to add the direction for each one, for each electric field line, which is going to be directed from positive to the negative. And that would be for the second configuration. And then they are asking you to do the same thing. They are asking you over here to describe what you are actually observing in that sketch. So again, over here you have semicircular shapes for the equipotential lines for that dipole. However, in the middle, since we have the same contribution of charges from that dipole, therefore you are going to have a perfect straight line for the equipotential line. And then you have the electric field lines, which are actually directed from positive to negative while being perpendicular to these equipotential lines. That would be regarding the description. Now, regarding the rest of the questions, they are somehow easy to answer. Over here, when they ask you what is the electric field inside the capacitor, meaning that you have actually to calculate it. So since we have a uniform electric field over here between these two parallel plates capacitor, meaning that E should be uniform everywhere. So it's only enough to find one value for E. And in that case, you can find the equation for E by going back to the equations that we have established during the lecture part. So we know that V is actually equal to the work over Q. And we know that the work is equal to the force times distance. And the force is none other but it's equal to E times Q times R over Q. Q and Q, they cancel, therefore we are left with the voltage equal to E times R, and R would be the distance in that case, or the separation between these two plates over here. Therefore the electric field would be equal to the potential difference over difference in distance. So delta V is what? Delta V in that case would be that potential difference between these two plates, and the potential difference would be actually the potential that you have applied through that DC power supply, and delta X in that case would be none other but the separation between these two plates. So having delta V, having delta X, you can find the value for that electric field, which is going to be actually uniform throughout that entire parallel plate configuration. Now in question number 6. Is it possible for two different equipotential lines or two lines of force to cross? First off, what do they mean by two lines of force? A line of force is basically the electric field line. So they are asking you if the equipotential lines or the electric field lines for the same voltage, can they cross? First off, you cannot have multiple equipotential lines for the same voltage, especially if you have only one power supply, one power source. So, for example, over here we started, let's say, at a value of 5 volts for that plate, and a value of 0 volt for the other plate. Let's consider that equipotential line over here, the first equipotential line, and let's consider that it has a voltage of 4 volts. First off, it is not possible to locate another equipotential line of the same voltage, especially that you have only one power source. It's not like you have two power sources that are being hooked over here and you have multiple voltages that are overlapping each other. First off, we have only power source, and that power source is going to give you only one voltage or one equipotential line for each voltage. So first off, we cannot have multiple equipotential lines for the same voltage. That would be a first. The second point is the equipotential lines, they cannot cross, meaning that if they have crossed, therefore they are overlapping, and if they are overlapping, meaning that you have two power supplies giving you two voltages, two similar voltages that are overlapping each other. So over here, let's say we have a second power supply and it's giving you also a voltage of 4 volts, therefore that other voltage is going to be overlapping that first voltage, and now you have two equipotential lines of the same voltage overlapping each other. But the question over here is not regarding that. The question over here is to have two different equipotential lines crossing each other. Two different meaning that they have two different voltages. So for example, the 4 volts over here and the 2.5 volts equipotential line overlapping each other. That is not possible at all. The equipotential lines of different voltages, they can never overlap each other, and they can never actually cross each other. And that would be actually the case also for the electric field lines, since the electric field lines are perpendicular to these equipotential lines. And that would be it for the equipotential lines and the electric field mapping report.